we've learned that the tensor product is a right-exact functor. And the defect of the failing left-exactness can be measured by another functor that we're introducing in this video, the Tor functor. Let me define this Tor functor or Tor terms. Let M be a right module over a ring R, and N a left module. So similar situation we have when forming the tensor product of M and N. Further, we consider a projective resolution of M by projective R modules. And then we can define the Tor group in degree I as the homology so here's the symbol Tor of Mn over R, and this is the homology in degree I of P star tensor N. Okay, so P star, the resolution is a chain complex. We tensor it with N, and then we have still a chain complex of abelian groups, and we take its homology. And this is the Tor term of M and N.
So sort of we throw away the M from the resolution, right? It doesn't appear anymore on the right-hand side.
Here on the right-hand side, there is, especially if R is a non-commutative ring, there is no R module structure left, if you mean that.
No, I meant that the module M, of which P is projective resolution, doesn't appear anymore on the right-hand side.
Right, it doesn't
so
appear
we throw
on the
M
right-hand
away.
side.
Yes.
I mean, it appears in disguise. Of course, it depends on M because we're choosing a projective resolution of M.
But then we only use the P part of that resolution.
Exactly.
So this is what I wanted to say.
Exactly.
Yeah.
So it's not symmetric the way I've written it here. Turns out that this Tor functor is symmetric. It turns out, and this is a theorem we're not going to prove, that you could do something similar on the right-hand side. You could projectively resolve N and then take M tensor projective resolution of N. That would turn out to be the same thing, but this is something to show. But maybe before that, a question arises, namely whether this is independent of the choice that we do here. And it is independent up to unique isomorphism. So if you choose another resolution, Q star of M, then you get a chain homotopy equivalence between these two resolutions by the fundamental theorem of homological algebra. So you get a chain homotopy equivalence between P star and Q star, which induces on H0 the identity of M. And therefore, you get maps between the Tor terms, which are actually isomorphisms. So let me write this down. If Q star to M is another projective resolution, then the identity on M is induced by a chain homotopy equivalence from P star to Q star, which is also unique up to chain homotopy. Okay, that's the fundamental theorem of of homological algebra that gives us this. And therefore, we get an induced map on the level of Tor terms, because if you have a chain map, you still have a chain map when you tensor with n. You can also tensor the chain homotopy with n. So a chain homotopy equivalence in particular, when tensored with another module, is still a chain homotopy equivalence. So we get this chain homotopy equivalence from P star tensor n to Q star tensor n, and therefore isomorphism between this HI group and the HI group defined by Q star. And moreover, there's not just any isomorphism between these two homology groups. There is like a preferred isomorphism, because that chain map, that chain homotopy equivalence, is unique up to chain homotopy. Chain homotopic maps induce the same map. So again, if you have another projective resolution, you have a priori a different definition here, HIQ star tensor n, but there is a preferred isomorphism between the two homologies. And in that sense, this definition is independent of the choice, and it's a well-defined object. Now, there is more philosophical question, namely, are you happy with such a definition? I think you alluded to that point in a previous video about the tensor product, that if you want to define an object, you really want a definition. you can say, okay, we defined it, and various definitions, they're all isomorphic up to unique isomorphisms, but it would be much nicer to say, well, here is the object, and it does not depend on anything.
But there are functorial constructions to get projective resolutions, I guess, and this is what one should do, right?
I'm not sure one should do it.
Or what
That's
could
actually
do it.
the definition to work with.
Yeah.
But you're right. There are canonical choices of projective resolutions which are functorial. So there are functorial choices of projective resolutions. That's one way, and then you can just say, this is my definition.
And we even saw it in the when you proved that projective resolutions exist. One can take that one, which is in fact a free resolution. Yeah.
Yes, you can make this into a functorial resolution. And then you can compute just any other resolution to actually compute these things. But there is another way to do it, which is a kind of silly trick whenever you are in this situation that you define an object up to unique isomorphism. So you could do the following. So to get something truly well defined, I emphasize the truly, because the other thing is also well defined up to unique isomorphism. One should always get skeptical in math lectures when there's a sentence like that. Right? It's truly well defined. One could define the Tor of M and N as the sum over all projective resolutions of HI P star M divided out by the equivalence relation that identifies two not two copies, that identifies two such homology groups via this preferred isomorphism. Okay, so HI P star tensor M will be identified with any other resolutions via the preferred isomorphism. So that gives you an equivalence relation. You can divide that out, and then of course what's left is just one copy. So this is still isomorphic to the previous definition, but by taking the sum over all projective resolutions, I can make it functorial in that sense. So that's stupidity that you can always do in such a situation. I want you to quickly forget about it and accept this definition that we have here as the right and working definition of the Tor term of M and N. So this Tor is a functor actually in both terms. It's a covariant functor. In both variables, meaning that if you fix a module, say here on the left, and you just consider this as a functor of the right variable, it is indeed a functor, and the same for the left. Okay, so why is that the case? Let's first discuss the functoriality in the second variable. So clearly, if you have a homomorphism from n to m prime, let's call it G, this induces a chain map P star tensor n to P star tensor n prime, just by the identity tensor G. And henceforth a map between the Tor terms. Because then you go to homology, you get an induced map from Tor mn to Tor mn prime for all I. Okay, so that's pretty easy. What about the functoriality in the first variable? So if you have a homomorphism from m to m prime, then we have the problem that m and m prime don't really appear in the definition explicitly. They appear in somehow in a hidden way via the resolutions. So we have to choose a resolution for n. Let's call it P star, and one for m prime, P star prime. And we can resort to the fundamental theorem of homological algebra once more, because we get up to chain homotopy, a unique chain homotopy, up to chain homotopy. We get a unique chain map from P star to P star prime, which induces on H0 the map F from M to M prime. And hence, a chain map between the tensor resolutions. Just taking this chain map tensor the identity on n now. And of course, this chain map then induces a map on homology, which is a map between the Tor terms mn and m prime n. And the notation is Tor F identity. So let's now investigate how this Tor functor repairs the defect of the missing left-exactness of the tensor product. So first let's relate the Tor functor to the tensor product at all. Lemma or proposition, this is actually a very easy statement, that there is a natural isomorphism, if you want, in both variables a natural isomorphism of functors between the Tor 0 of Mn and the tensor product over R of these two modules. So let's prove this. We need a projective resolution of M for this purpose. So let's consider P star, projective resolution. And then we know how to compute left-hand side. So left-hand side, you obtain by taking the co-kernel of this map, right? So this is the tensor chain complex, and the homology in degree 0 is just everything divided by the image. So it's the co-kernel of this first map. Remember that this is a resolution, so this is exact, okay? I mean, it goes on, there you get a resolution of the whole M, but we're just interested in the first two steps of this projective resolution, and in particular, this is exact. So since this is exact, and the tensor product with n is right exact, we can put here m tensor n and still have an exact sequence. So let me write it down. So if we just look at the beginning, and this is still exact. Okay, remember, I'm not claiming more. If I would consider the next step here, I'm not claiming that this sequence is exact at this position. And in general, it won't be. I'm only claiming that this here is exact, and that just follows from the right exactness of taking the tensor product with n. And this is all we need, because now we described this m tensor n as the co-kernel of this map, and I already said that the co-kernel of that map is exactly h0 of p star tensor n, so this is exactly the Tor term in degree 0. So the next theorem states a long exact sequence for the Tor terms. So let the following be a short exact sequence of R modules. Let n be a left R module. So these are right R modules. I mean, admittedly, 99% of the time we will be talking about commutative rings and then it doesn't matter. But everything I say does work, for non-commutative rings. And in that situation, there is a long exact sequence of the Tor terms. Let's call this 0. Then there is a boundary map here. So let me bring this up. The first terms that you see here, they are induced by the maps from M0 to M1 and from M1 to M2. Then there is a boundary map that brings us to Tor 1. Tor 1. Again, there is another boundary map. The scheme repeats. And now I could write Tor 0, but we know that Tor 0 is the tensor product, so let me write it with the tensor products. And then it adds, okay? And should be clear how this continues to all the higher Tor terms. Now this explains what I said before about repairing the defect of left exactness. Taking the tensor product with n in this short exact sequence, M0, M1, and M2, does give you at least a sequence which is exact on the right-hand side, so it will have a surjection. I mean, this will be a surjection. But this is not necessarily injective anymore, but the degree to which it is not injective is measured by the Tor term, and more precisely, it's not just one Tor term, but this will be embedded into this long exact sequence. In particular, if this Tor 1 term vanishes of M2, you would get that this map is injective. Now you consider a short exact sequence for the second variable, n0 to n1 to n2. So these are left R modules. And then we have a natural long exact sequence. Let me not indicate the Tor 2 terms. It's pretty clear how the scheme looks like. First, we have the maps induced by the maps of modules. And then there is a boundary map here on the right-hand side, and it would go to Tor 0, but I write Tor 0 by the tensor products. course, it also gives you a similar interpretation of these two terms as a kind of measure of defect of injectivity on the left-hand side.
So in particular, it means that if one plugs in a flat module in either of the variables of Tor1, one gets 0, right? Because one wants the sequence to be exact. I mean, the sequence of tensor products. Yeah,
that's correct. Yeah. I mean, another way to see that, even before having this long exact sequence, is by terms of the definition. So the Tor term here, what you do is you have a projective resolution. Projective resolution does not have homology in higher degrees by definition. And now you tensor with a flat module. So the exactness is preserved by tensoring altogether. And if you form the homology, the higher homologies from degree 1 on have to be 0. So you can see it right from the definition. Of course, you can also see it by arguing from the long exact sequence.
Yeah. So in all degrees, the Tor term vanishes.
In all
for
degrees,
a flat
the
module.
Tor term vanishes. If you have a flat module in either variable, either the left or right variable. To prove this fact about the long exact sequence, we need a lemma that appeared in the exercises.
Though not by the name, so that you couldn't Google it.
What's the name?
It's again? The Horseshoe lemma.
The Horseshoe lemma. Yeah, thank you. So now that you can Google it. And I will state the lemma, but I will not prove it. I invite you to prove it yourself. So let M0, M1, M2 a short exact sequence. And the statement is that there are projective resolutions. Resolutions P star I to Mi and chain maps from P star 0 to P star 1. Such that if you put everything together, you get a commutative diagram. So let me draw here the beginning of the resolution. No, I need more space. Here's the resolution of M0, next the resolution of M1. And finally, M2. So these maps we have anyway, this short exact sequence here, and the statement was that we have chain maps between these resolutions such that everything commutes, and in addition, on each row we have short exact sequences.
Even split short exact sequences, right? Because those are projective modules.
That's true.
So really the middle projective resolution is the direct sum of the outer projective resolutions.
That's true. That's true, and that gives you also an idea how to prove that lemma. Because what you do, and that's a hint that I will give now, you start with arbitrary resolutions on the left and on the right. I mean, there is no better choice anyway. And then you know that degree-wise, this has to be isomorphic to a direct sum of the two. And then the whole matter is then you have a guess for these modules, just the direct sums, and then you have to find these maps that put everything together and make this into a short exact row, and also into a resolution of the middle term M1. And that's what you have to prove here. So you can extend the short exact sequence of modules to short exact sequences of projective resolutions. That's the statement. I won't prove it, but I will use it now in the proof of the statement about the long exact sequences of the Tor terms. Remember, there were two cases, and the first case was about having a short exact sequence in the first variable, and this is where we need the Horseshoe lemma because we have to compare homologies that involve projective resolutions of the first variable. So choose projective resolutions as in the Horseshoe lemma. And since, and you already mentioned that, the rows in the diagram above split but we also get from this that if we tensor with n, we still have something short exact in each degree. In other words, what you see here is a short exact sequences of chain complexes. Because if you have a split here in each degree, also after tensoring you have a split, and this split induces this direct sum composition of the middle term in the two outer terms, and then still having the split, everything gets preserved after tensoring with n. You still get this direct sum decomposition of the middle term by these two outer terms, and that is gives you the short exactness of this sequence. Somehow I don't think I explained that too well, so let me give it another try. You know that having a split here is equivalent in this setting of abelian groups to a split here. So you get a split map from P1 to P0 in each degree that is such that if you go that way, it is the identity. Of course, this is preserved after tensoring with n. So if you tensor with n, you still have a map back. Tensor, you take the original split, tensor the identity on n, such that if you go like that, it is the identity. And that shows you that you have injectivity here. And the injectivity here is the only point. All the other things here are still, I mean, it is right exact. So you have to check the injectivity here. And this is coming from this split from P1 in some degree star to P0 star. Okay, I think that's a better explanation. In any case, we have a short exact sequence of chain complexes, and for any short exact sequence of chain complexes, we can consider the long exact sequence in homology induced by that, and that long exact sequence is exactly the long exact sequence that was stated in the claim. Because the homologies of these things are just the Tor terms associated with m and n. And in the long exact sequence statement above, I just wrote the Tor 0 terms as the tensor product. So we're already done. for the long exact sequence associated with this short exact sequence. Proves the first statement. What about the second statement? This was about having a short exact sequence in the second variable. And that should be even easier. Don't need the horseshoe lemma for that. Just need one projective resolution of the module M. And then we consider this sequence here. So we tensor the short exact sequence for the ni's with the resolution. Then definitely this is exact in each degree. What about here? Why is that injective? Well, now we can argue by saying, well, P star consists of projective modules, and tensoring with a projective module is an exact functor, so we have a 0 here.
We showed a proposition saying that projective modules are flat, yes.
Yeah. So this is exact by projectivity of the P stars. And now the long exact sequence associated with star star yields the statement. Long exact sequence in homology associated with star star yields statement 2. Let me now state some general properties of the Tor terms that extend the properties we already have for the tensor product. So Tor commutes with arbitrary direct sums. In both variables. And that's something we already have for Tor 0, which is the tensor product. Let me only say what I mean by that and not write down it in a formula. So if you have, say, in the first variable, you have a direct sum of mi's, in the second variable, you have a module n, then Tor of this direct sum and n is canonically isomorphic to the direct sum of the Tor terms of mi and n. And the same for the second variable. The proof is actually very easy. So in the second variable, what you do, you start with a projective resolution of the first variable, and now you tensor with a direct sum. But since tensoring is compatible with taking direct sum, this is a direct sum of chain complexes, and the homology is therefore also direct sum. So it's very easy to see that this is true. For the first variable, if you have a direct sum in the first variable, you just choose for each summoned projective resolution, and then the direct sum of the projective resolution is a projective resolution of the sum, and then you argue the same way. So this is something that you might want to think about it in a quiet minute, but it's very easy. The second statement is less easy to prove. But I want to state it. If R is commutative, which means that we don't have to distinguish between left and right modules. Each left module is in a canonical way also a right module. Then the Tor is symmetric isomorphism, or naturally isomorphic. I only want to make the remark that somehow we didn't during the discussion of the tensor product, that for I equals 0, this is the statement that M tensor n is isomorphic to n tensor m, which is of course true, and the isomorphism is given on the level of elementary tensors by mapping M tensor n to n tensor m. And to prove it for the Tor terms is, it's actually a bit more involved, and I only state it. So let me present you a computation of Tor terms. We knew from the previous video how to deal with tensor products of finally generated abelian groups. We could have even stated these computations for principal ideal domains. So it's very easy to write down for any finally generated module over principal ideal domain what happens for the tensor product and also for the Tor term. And this is what I want to do next. In particular, most important case will be the ring Z, which is a principal ideal domain. That's the abbreviation for principal ideal domain. And then we have the following computations. Again, if you don't feel comfortable with this generality, just think of the ring Z. So for all modules, now we're in particular in a situation where R is commutative, so you don't have to talk about left and right. And it so happens that the Tor terms vanish in degrees at least 2. So there's only Tor 0 and Tor 1. Second statement, when you have a principal ideal domain, then you have the inclusion of the torsion submodules into these modules. And I want to look at these inclusions for M and N. And M and M should be finally generated R modules, because in that situation we have a structure theorem like we have for finally generated abelian groups. And these inclusions of the torsion submodules induce isomorphisms on the Tor 1 terms, I mean the only remaining Tor terms. And that's what I meant when we had this discussion before, that M and N, the Tor term, only depends on the torsion in that situation, and I think that explains the name.
Yeah, this is what I had in mind, but it's of course nonsense in degree 0, it's in degree 1.
Yeah, it's in degree 1.
Yeah.
And finally, a concrete computation. So let R and S be non-zero elements in our ring. And let D be the GZD of R and S. So also in a principal ideal domain, that makes sense. So what I mean is that D is an element that generates the ideal generated by R and S. It's a principal ideal domain. We know that any ideal, also the ideal generated by the two elements, is generated by one element. And we take, it's not necessarily unique, but we take one such element, D, And this plays the role of the GZD in the case where R is just the integers. And then the following computation holds true. So if I divide out these ideals by R and S, then Tor1 is just R mod D. And similar computation we had for the tensor product. Okay, we only formulated it for the case Z, but it's the same. So also for Tor0, you have the same result, Tor0 being the tensor product. So not only depends this Tor1 term only on the torsion, also the output somehow is torsion, is a torsion R module. That gives you the complete picture for finally generated modules over principal ideal domains, and I want to finish this lecture by giving you proof of that theorem. So the first theorem said that Tor I is 0 starting from degree 2. So let's consider module M and N, in particular M, and start by developing a projective resolution. And how do you start doing this? You remember how we constructed projective resolution. You start at the very first step with an epimorphism. And you can take now a free module to the module M. Oh, let's write it like that with a double arrow. Take an epimorphism to M from a free module, finally generated. No, not actually, just a free module, from a free module, because I don't assume that M is finally generated. And then we got a projective resolution by mapping a free or projective module onto the kernel of this P. This is how we went along, and this is what I want to consider now. I want to consider this kernel. So this is obviously, by definition, a short exact sequence. If that kernel would be automatically projective or even free, then we don't have to choose anything to project onto it. We could take this kernel as the next step in the projective resolution. And this is what happens for principal ideal domains. For principal ideal domains, a submodule like the kernel of P is free as a submodule of a free module.
So in fact, you show something a little stronger than just saying that the higher Tor terms vanish. You show that every module over a PID has a projective or even a free resolution of length 2.
That's true. Exactly, because we have injectivity here. So this is a free resolution of M, and now it's completely clear that there are no Tor terms in degree starting from 0, from 2, because there is no module there. All the modules are 0. So this fact for principal ideal domains is of course something that we won't prove now. That's a fact from algebra. I don't know, what's your favorite book? Where to look this up?
I don't know.
There are many.
It's for sure in Bosch and
Yeah.
in Lang.
And this implies the first statement. What about the second statement? The second statement, to remind you, was about the fact that the Tor term only depends on the torsion submodules in the case of finally generated R modules. And from the structure theorem about modules, finally generated modules over a principal ideal domain, we know that such a module decomposes the direct sum of its torsion module in a free part. Again, a fact from algebra that we freely use. So in the finally generated case, we have this direct sum decomposition where Fm is free. And then the claim follows from two facts. Well, it follows from the fact that the Tor term is compatible with taking direct sums in both variables. So follows from the fact that Tor commutes with direct sum. And then you also want that somehow the free parts here don't contribute anything, they only contribute 0, but this is also correct. So it also follows from the fact that, that Tor vanishes for free modules. We discussed this before, that if you have if you plug in a flat module into one of the variables, then in particular, let's say in the second variable, you get immediately that tensoring with that flat module here, it's even a free module. The projective resolution of the first variable stays exact, therefore taking homology gives you 0. If the projective module is in the first variable, you could either appeal to the theorem that says, okay, the Tor for commutative rings doesn't depend, it's symmetric, but that's a theorem that's a bit more complicated. But you could also argue by saying, well, if in the first variable I have a projective module, then this module is a resolution of itself of length 0, and there are no higher Tor terms, not even a Tor 1. In both cases, with both argumentations, you get that for free modules, the Tor vanishes, and the only thing that remains is the Tor of the torsion subgroup of M and the torsion subgroup of N, and that computes Tor Mn. So this proves 2. The third statement was a concrete computation, very similar to the computation we had for tensor products, and I will be brief here. So we start as for the tensor product by considering a short exact sequence that is not just a short exact sequence, you can also view it as a projective resolution of this module here on the right hand side. If we tensor this with R mod S and take the homology, we can compute the Tor 1 term of these two modules, R mod R and R mod S from that. So how does the long exact sequence look like? There are no Tor 2 terms. Let's take the other pen. So here there would be the other Tor 1 term, but they would involve a free module of rank 1, so they're all 0. So the long exact sequence here to the left is actually just consists of zeros. And then you have Tor 0, which is just the tensor product we're looking at. And finally, we have this. And there's a 0 here. Now, the tensor products are taken over R. So we know that this is just R mod S. and it's still multiplication with R. And now you see that this Tor term that we want to compute is just the kernel of this map. So in the previous video, in the special case of R being the integers, we computed the tensor product as the co-kernel of that map. Now you have to compute the kernel of that map, but it's still an elementary exercise that the kernel of this map is just R modulo this D, which is the GZD of R and S, and I won't do that computation now, but that finishes the third statement.
Kernel and co-kernel are isomorphic for this multiplication map.
Yeah.
It's funny.
It, by some coincidence, they're isomorphic. Well, okay, I could say why it's not a coincidence, but let's finish this. So hence Tor is isomorphic to this kernel. And this is isomorphic to this by a small exercise that I leave to you.